This is the first in a series of videos on the new SQUID3 software with the goal of introducing the shrimp community to its functionality. Subsequent videos will have more how-to information, including how to import your data and perform custom calculations, but today we'll start with a complete start-to-finish SQUID geochronology project file in order to give a short tour from start to finish. I'll begin by opening the demonstration SQUID project that comes preloaded when you downloaded SQUID3. This file is derived from a shrimp XML data file from a typical uranium-led geochronology session here at the Geological Survey of Canada. As you begin playing around in SQUID3, you'll find that as a general rule you want to navigate from left to right through the menus. Under the Manage Project tab, which is where we are now, there are a number of preferences that you can set which will be very familiar to users of SQUID 2.5. For example, setting whether or not you want to do secondary beam normalization or setting your minimum error on your calibration correction. Under the Project Manager, you can also set the default common lead model you wish to use to correct the reference material, and what model you wish to use for physical constants, such as decay constants. There's more to say about models, and this will be covered in a separate video. This SQUID3 project file has parsed an XML data file and has identified the names of the samples within that file based on either a delimiter or the number of characters in the sample name. Once you've defined your sample names, you're able to select one of them as your reference material and assign it a model to that reference material that contains the information required for the calibration. You can use the same reference material or a different one for your concentration calculations. Under this Data tab, you can also audit your data, viewing the session at a glance to see any jumps in mass offsets. You can also investigate things like primary beam intensity. And if you see any problems or analyses that you might like to remove, you can do that here in this Audit Data function. And you do that simply by clicking on the analysis in question and then right-clicking to be able to remove the selected spot or do different things. Continuing downstream to the task menu, this is analogous to SQUID 2.5, where you define the ratios and the calculations that you wish to carry out. There are three ways to create these tasks. You can load a pre-built one from the task library, you can load an old SQUID 2.5 task, or you can load a custom SQUID 3 task from a folder. For now, we'll just tour the task that's associated with this file. Here you'll find information similar to the general uranium-lead equations panel in SQUID 2.5 tasks. This includes an audit that allows you to check that the species in your file match the species in your task. It's here as well that you'll find details like what equation is being used to calculate the calibration constant. A task, though, consists of a group of expressions, and those expressions are shown in the Expression Manager window here. This is, for all intents and purposes, a series of equations. These are categorized in this accordion on the left for easy navigation. Each expression can be individually examined, and this provides for the first time transparency into the math that's under the hood in SQUID 2.5. There's a category called Custom Expressions that contains user-defined equations that are separate from the basic package of geochronology equations. And these custom expressions are editable. They're shown in the top box as text and in the middle as a typeset image for readability. The output of a saved expression is shown in a peek window in the lower right. This means you can instantly evaluate your expression for errors. This is a huge improvement over SQUID 2.5, where you had to run the full data reduction scheme iteratively when troubleshooting your task. Moving on, under the Common Lead menu, you can set the type of 204 overcount correction you wish to do using the 207 overcount correction, 208 overcount correction, or the original 204-206 ratio. And then you can assign the common lead composition you wish to use to correct your unknown samples. You can do this by applying a common lead model, so a fixed common lead composition, Stacy Kramer's composition at a given age, or a Stacy Kramer's composition that is tuned to each sample. And of course, you can always apply different corrections to different samples. The results can be visualized on Concordia diagrams, as you can see here, or as weighted means. The Concordia plots can be saved as SVG images. The weighted mean stats, so the value, the error, the MSWD, and so on, can be written to a text file and output. In terms of getting the data out of SQUID, there are a number of canned report formats, but probably the one that you'll use the most is this report builder. Using this, you can output your results using the default format or build and save your own report format for standard data and reference materials, or rather unknowns, separately. The parameters menu is where you can build or edit models, including your common lead model, reference material model, and physical constants models, such as decay constants. In the About window, you'll find online resources, including a link to the GitHub repository, where the source code resides and where you can download the latest version. There are also links to the development notes, which include detailed documentation on the SQUID 2.5 algorithms, which were used as a basis for SQUID3. And finally, under the Help menu, you'll find a link to this YouTube channel where I'll continue to post more videos, as well as a direct link to the Issues function on GitHub, where you can provide suggestions, report bugs, or ask questions, which we strongly encourage you to do. Happy squidding!